Hi everyone, my name is Rachel Doring and here is the results and processes for Lab 2 on lines of distributed charge. The overall purpose of the lab was to determine the approximation of the excess charge left on a piece of charged clear tape. We needed to calculate the total charge on one piece of tape using the same data and results from Lab 1 and modeling it computationally using a different method. To gain this data, we placed two pieces of tape on top of one another and quickly ripped them apart. Doing this gave the top piece of tape a charge. We then repeated this process to create two identical pieces of charged tape and oriented them so one can hover above the other. Some key concepts and physical principles that were used in the lab were Newton's second law, which helped us determine the electric force acting on the tape by calculating the gravitational force, Newton's third law, which states that with every action there is an equal and opposite reaction, the electric field of a uniformly charged rod, and the superposition principle. By breaking up the tape into multiple point charges and using the superposition principle, we can calculate a much more accurate value for the electric force. The most accurate value would come from using an infinite amount of point charges and integrating to find a final answer. Here is the data that I collected during Lab 1. The mass of the tape was 2.032 times 10 to the negative 6 kilograms. The gravitation force was 1.99 times 10 to the negative 5th newtons. The hover distance between the two pieces of tape was 1.5 centimeters, and the calculated value for the charge on the tape due to modeling the entire piece as a single point charge was 7.05 times 10 to the negative 8 coulombs. Some assumptions that were made during the duration of this experiment were that both pieces of tape have the same net charge and that the charge is evenly distributed along the entire piece of tape. For this lab, we were given a starter code, which we could then adapt to fit our own data and calculations. The code utilized multiple for loops and nested for loops that allowed us to iterate through lines of code to produce multiple point charges. I chose to model the tape using 10 charges, though the final answer would have been more accurate with more point charges. The for loops also allowed us to create separate force vectors for each of the point charges and add them together to get the final force vector. In the model, you can see the charges in red representing the top piece of tape and the charges in blue representing the bottom piece. The charges are separated by a distance of 1.5 centimeters as measured during Lab 1. The large yellow arrow represents the gravitational force acting on the top piece of tape. The large white arrow, which is equal in magnitude to the gravitational vector, represents the net electric force acting on the top piece of tape by the bottom piece. Each of the green arrows represents the electric field acting on each individual charge. By summing each of these green vectors, we found that the net electric force is 1.99 times 10 to the negative 5th newtons. In order to get the magnitude of each of the large force vectors equal, I needed to play around with the value of Q. I finally found that the value of Q to be 7.492 times 10 to the negative 1 coulombs. The overall net charge on the tape as calculated in Lab 1 was 7.05 times 10 to the negative 8 coulombs, while the overall net charge of the tape as calculated in Lab 2 was 7.49 times 10 to the negative 1 coulombs. The overall charge as calculated in Lab 2 is much larger than the value calculated from a single point charge, because, due to the fact that the magnitude of the force and the distance are fixed and will remain small, and some components of the force vectors will cancel out, the magnitude of the charge needs to be larger to compensate. If I had modeled the charge on the tape as a single point charge, the calculated value for Q would have been exactly the same as the value calculated during Lab 1. The values found in each of the labs differ because we are superimposing multiple electric force vectors acting on the top tape from the bottom, which simulates a more distributed charge as opposed to the force coming from a single point in space. In reality, the charge on the top tape is evenly distributed along the length of the tape, so modeling the experiment using multiple point charges simulates the experiment as a much closer version of reality than a single point charge.